Hello friends, in this lecture we will discuss about another type of time domain filtering method, that is derivative based operator. The derivative based operator in the time domain is mainly used to remove low frequency artifacts, for example baseline drift. Whereas if you compare with the filters like synchronous averaging or moving average filters, they are mainly to reduce high frequency noise. Derivative based operator removes the parts of the input that are almost constant. We know that if we take the derivative of a constant, it will be 0. So in this case also, mainly it will remove the noise or input, the parts in the input which are almost constant. And large changes in the input leads to high values in the output of the derivative operator. Derivative based operator is a kind of moving average filter, but in this some of the coefficients will be negative, as you can see in the simplest form of this derivative based operator. In this, the derivative is obtained by taking the difference between the present, that is means xn, and the past input value, that is x of n minus 1, and the corresponding, if I want to calculate the transfer function of this, what will be the transfer function? We have to calculate using Z transform. So it will be Hz is equal to 1 by t 1 minus Z inverse. Now to obtain the frequency domain representation, again we have to keep Z as e raised to power j omega t, and then we will obtain h omega as this equation. We have to simplify using the identity. In last lecture also we have discussed about that identity, e raised to power minus j omega is equal to cos omega minus j sin omega. So similarly we are using here also. Now from this frequency response we can calculate again the magnitude response and the phase response. Now if you see the magnitude response, it has sine function. That means it will be 0 at omega equal to 0 and slowly it will rise. That means it will be a high pass kind of filter, and also it will have linear phase but in decreasing order, because here we have minus omega by 2. Now let's see the figure which shows the magnitude response versus frequency and the phase response versus frequency. This filter is good in removing the DC component as well as the low frequency artifacts, but at the same time it will boost high frequency components, or I can say high frequency noise if present in the signal, which is not a desirable characteristics. So this filter needs modification, and one such modification if we talk about is a 3-point central difference operator. What we are doing in this, what change we are actually implying, what we are in this, if you see the equation, in this we are taking the average of two successive output values, that means yn plus again the what is the past output y of n minus 1, we are taking the average of these two to obtain a new signal, that is y3n. Now if we replace the equation of yn and y of n minus 1 in terms of x using the derivative based operator, you will find the equation as equation number 5, 1 by 2t, that is xn minus x of n minus 2, and the corresponding transfer function will be hz is equal to 1 by 2 1 minus z inverse 2. Now if we factorize this, you see we have obtained two factors. It can be observed from this that the transfer function of this 3-point central difference operator basically is the product of the transfer function of the simple first order difference operator, if you see the first factor, and a 2-point moving average filter if you see the second factor in equation number 6. That means we can say these two filters, first order difference operator and a 2-point moving average filter, in series, they are connected in series, or we can say cascade, to obtain a 3-point central difference operator. Now let's see how the magnitude and the phase response vary with frequency. One thing more you can notice here, these factors, basically when you simplify these factors you will get two poles. or two zeros. One will be at z equal to 1 and other will be at z equal to -1. That means it corresponds to a band pass type of filter. Now let's see the magnitude and frequency response of this. So now if you see the magnitude response, it is peaking in the middle and it is 0 at both the end. So it will help to filter out low frequency noise like baseline drift, and also at the same time if there is any high frequency noise or high frequency component, it also gets suppressed. And if you look at the phase response, it will preserve the property of linear phase because it is decreasing but it has again the linear phase. So we can say that this type of filter is much better in real life applications. So this was all in this lecture. Thank you so much.